This is lesson 2 in chapter 27. You might recall a lab that you did several months ago, a lab in which you calculated or determined experimentally the wavelength of laser light. And the way that you did that was by shining laser light through a diffraction grating. Now, a diffraction grating is like a piece of exposed film where someone has taken like a razor blade edge and etched lines extremely close together, parallel lines in that material. And when the light goes through that material, it diffracts. Now, there's a very important point in order to see diffraction, and that is that the spacing between the lines of the diffraction grating must be approximately equal to the wavelength of the radiation to be measured. So imagine that we have rays of light, thinking about light as being made out of waves, traveling in this direction, and this right here is my diffraction grating. Now, if this space, and I'm going to use a different color to show that space, if this space here between the waves is approximately the same or in the same ballpark as that space, then when the waves strike that opening, you will see them diffracted like this. That's what this statement is saying, that the spacing between the lines right there must be approximately equal to the wavelength of the radiation. There's your wavelength right there. Now, another way to accomplish diffraction, instead of shining it through a diffraction grating, is to shine light through a crystalline structure. And once again, in order to see diffraction, the wavelength of the light, this distance right here again, must be approximately equal to the spacing between each of the particles, like cations and anions, positive and negative ions, in the crystalline structure. When this happens, you get a two-dimensional pattern of cancellation and reinforcement called a Lauer pattern. It almost sounds like there's an R at the end of that word, Lauer pattern. And that Lauer pattern looks something like this. You have all of these dots representing exposures on this photographic film. And you'll notice that it forms a pattern. They're not just a random dots scattered all over the place, but there is an arrangement to those dots because the crystal has a regular pattern or geometrical arrangement of the atoms or the ions that make up that crystalline structure. And then your X-ray crystallographer, as they gain experience and become an expert, would be able to look at this photographic film and the dots that are left behind, the Lauer pattern that is left behind, and identify what kind of crystal made that pattern. In this case, you're looking at a crystal of sodium chloride, which of course is a three-dimensional structure containing positive sodium ions and negative chloride ions, as you can see right here. So as your light is entering the crystal and striking the crystal, sometimes some of the light will hit a particle on the surface. It could be a cation or an anion. Some of the light, now I'm using these lines as rays instead of waves, might miss a particle in the upper plane, but strike a particle in the next plane down, or the next plane down after that. And as a result, you create that Lauer pattern on a piece of photographic film. Now, the equation that you used when you were trying to find the wavelength of laser light looks something like this: d sine theta over m. And you can see it's very similar to this equation right here. This is called Bragg's law. And if the wavelength and the diffraction angle are measured, you can use this to calculate the spacing between each layer of atoms in the crystalline structure, which of course would be a fundamental clue as to what kind of crystal the X-rays are impacting. Now, this technique of identifying crystalline structures by using X-ray diffraction is perhaps most famously remembered because it helped us to elucidate the structure, particularly of DNA. People have known about, or scientists have known about, this chemical called DNA for a long time, since the early part of the 20th century. But it wasn't until the early 1950s that they figured out the structure, the crystalline structure of DNA. That it was, in fact, what we now call a double helix. Or we could say it's like a spiral staircase. Or we could say it's like a ladder that is twisted around some vertical axis. And by the same token, we can also now use that to determine the structure of RNA. By the way, an angstrom is 10 to the minus 10th meters, or it's a tenth of a nanometer. And that we need to use X-rays because X-rays have extremely small wavelengths that are in that same vicinity. Now, the people involved in this monumental discovery that sort of altered the trajectory of biology and many other fields were, first of all, Rosalind Franklin, in the year before I was born, who actually did all the hard work of gathering the data and taking the X-ray diffraction images and being really, really, really careful in her laboratory work so that her results could be reliable. But unfortunately, because she died kind of early in her life, and also probably because she was a woman back then, two other guys, Watson and Crick, sort of got all the fame and the glory for this figuring out of what the structure of the DNA molecule was. They got the Nobel Prizes, and unfortunately, 7 years after Rosalind Franklin did all of this hard work that Watson and Crick took advantage of, she died of cancer at a very young age of 38. Now, and they don't give Nobel Prizes after you're dead. In any case, Watson and Crick were not the nicest people in the world when you begin to read some of the things that they've said. Some of their quotes seemed rather racist. In fact, James Watson, who's not alive anymore, but Crick, who I think still is alive, he was very, very famous, but recently his name has been dropped from the Cold Harbor Research Station in New York because of some of the things that he said that were rather racist. Both of them were rather sarcastic as well. Both of them, when they saw the elegance of this DNA structure, and when they realized right off the bat very, very quickly that the structure of this DNA molecule, as you see it right here, with that double helix, lend itself to the obvious implication that when DNA makes a copy of itself, when a cell is undergoing division, it basically unzips. And so you have two strands, and then each strand has RNA bring the necessary nucleotides to each half of the strand. It would split right down the middle, which would actually be kind of a curlicue. And you would now have two DNA strands when originally you only had one. So this really began to unlock the genetic code and how the genetic code replicates when cells divide. Now, just in case you have forgotten, what you see here in the red are alternating sugar and phosphate molecules. Deoxyribose if you're talking about DNA, and ribose if you're talking about RNA. Actually, deoxyribonucleic acid, because it has a sugar deoxyribose in it. And that represents the rungs of your ladder. Then all of the blue things in between that you see here are the base pairs. And so one strand would have base pairs, the other strand would have base pairs, which is why we call them a pair, because there are two of them together. And those two of them are always these four. And we've learned that adenine and cytosine always pair up, and guanine and thymine always pair up in DNA. In RNA, we use uracil instead of thymine, or I should say that's the base that is used instead. And so it's this sequence of base pairs here and here and here and here that is the genetic code. There is absolutely no natural law that says if you've got this base pair here, the next base pair has to be such and such. We do know that the connections between the bases are hydrogen bonds, and we do understand how the sugars, if I change colors again, how the sugar and the phosphate and the sugar and the phosphate and the sugar and the phosphate that make up the backbone of DNA are connected, but the information is coded in the sequence of base pairs. And there's no rule that says what they have to be, because if you had lots of rules, you couldn't have a code. And that became the big question. Where did this code come from? Who wrote the code? How did this code come to be? It's a powerful argument for design. And Watson and Crick knew it. And so what they did is they said, well, this obviously looks designed. It's not something that could happen by accident or chance, regardless of how long you might give it. And so therefore, it must have been dropped off. And Watson and Crick had similar but competing theories about this. One of them said it must have come in on dust from outer space, stellar debris. And the other suggested that it was dropped off by aliens. And all that does, of course, is beg the question, well, how did it get on the dust, or where did the aliens get it from in order to bring it to the Earth and to plant this DNA so that, according to the broader macroevolutionary theory, evolution could take over, and after enough time, lo and behold, here we are. Very interesting history if you ever get a chance to study that. Now, just a passing word on the Compton effect. The Compton effect is the observation that when you have a high-energy photon, and I'll make it look like a particle with a blue dot, that strikes an electron, and so I'm going to change my mind. The electron is going to be the blue dot, and I'll come back here and erase that, and I'm going to make the photon red. When a high-energy photon, an X-ray photon, strikes an electron, the high-energy photon is deflected, but it doesn't have quite as much energy as it did before. Meanwhile, your electron is scattered, is deflected, and what Compton did, to his credit, is recognize the fact that this X-ray photon must be carrying energy and momentum and behaving like a particle, so that when it collides with an electron, energy and momentum are both conserved. You might remember way back in October, we talked about the conservation of energy in a glancing collision. And we measured that we used the conservation of energy to measure things like the angle maybe between the two deflected particles or what their velocities might be given the initial velocity. But the point is that momentum is conserved even when a photon strikes an electron. And once again, this supports the idea that light is packets of energy called photons. That's the particle part of the model, with wave-like characteristics. In other words, you can find the frequency and the wavelength. Now, we move on a little bit farther, and another scientist, Louis de Broglie, in his doctoral dissertation, which hopefully some of you guys are going to be doing in, let's say, 5 or 6 or 7 years, perhaps, had the idea of in thinking about the fact that maybe if photons have wave and particle characteristics, maybe matter also has wave and particle characteristics. If light is packets of energy called photons which have wave-like characteristics, maybe matter, which we typically think about as being particles, also has a wave-like characteristic, such as a wavelength. And this is about 100 years ago. And so if we look at the de Broglie wavelength equation, one of my favorite equations just because it's just so amazing, here is your mass times velocity, which we understand to be momentum. And we usually think of particles as having momentum. Here is wavelength. We think of waves having this wave characteristic, wavelength. And here they are together in the same equation. And so just like if I have a wavelength of light, I can calculate the momentum of that light. The same ought to be true according to de Broglie, and this has been confirmed, that if we had an atom Wainwright fastball and we measured its mass times velocity, that is to say, its momentum, that we could calculate the wavelength of that baseball or whatever the particle might be. Now, of course, the wavelength that you get is impossibly small to measure. But this idea of the dual nature of light is now extended into the dual nature of matter. Another application has to do with the electron microscope, which instead of using extremely small wavelengths of electromagnetic energy, it uses even small wavelengths. That is to say, it considers the electron as being a wave with a wavelength that is even smaller, and so you can resolve even smaller and smaller things with your electron microscope that you would not be able to resolve. In other words, it would look, in a sense, way too pixelated, but you would get your finer detail using electrons as waves instead of electromagnetic radiation as waves. And typically, wavelengths of electrons in an electron microscope are smaller than visible wavelengths by a factor of about 10,000. 10 to the minus fifth or 10,000 times smaller, so you can gain an advantage. I'm sorry, this is 100,000. Thank you. This is 100,000. And you can look at smaller and smaller things by using an electron microscope. And we have variations of that. This idea of a wave function is picked up in chapter 28 in quantum mechanics and atomic theory. And the idea is that anything that is a pattern or a regularity ought to be able to be described by an equation. And Schrödinger's equation is an effort to calculate the probability of finding an electron in a certain region of space about its nucleus. And it turns out that the wave function is designated by the letter psi, but it's psi squared that is actually a calculation of its probability of finding that electron in that particular region. And I talk more about this in chapter 28. They often hear quantum mechanics scientists talking about the collapsing of the wave function as you identify with a certain degree of probability where an electron might be. The last thing in this chapter is to talk about what is called the uncertainty principle. And the uncertainty principle is not the idea that we're uncertain what the principle is. The uncertainty principle is that, as a matter of principle, the act of measuring inherently has some degree of uncertainty. And it has nothing to do with significant digits, and it has nothing to do with the fact that all measurements are rounded off, and it has nothing to do with the fact that we need better and better measuring devices in order to eliminate uncertainty. It means it is a function of measurement. It is a property of doing science. It's something that no scientist can ever avoid, and that is that when you do an experiment in some way, often undetectable, you alter the very thing that you are studying. And I actually talked about this in my chemistry classes when we talked about the uncertainty principle. And when you look at somebody, because light is bouncing off of them, how do you know that the light isn't actually altering them in some undetectable fashion? And theoretically, you don't. And this is the work of a German physicist, Werner Heisenberg, during the first 3/4 of the 20th century. It's called the Heisenberg uncertainty principle. And the first part of it, the most famous part of it, is this. It follows this equation right here. A times B is always greater than or equal to C, which basically says, sorry about that, as A gets bigger and bigger and bigger, B has to get smaller and smaller and smaller. Well, applying it to the Heisenberg uncertainty principle, A is delta X. And delta X is position. And if you want to know the position really, really, really accurately, with very little plus or minus room for error, then you want as small a delta X as you can get. You want to make delta X smaller and smaller and smaller. The wiggle room of uncertainty in the position of X, you want to be very, very small. And you can do that, but there's a trade-off. The trade-off is you're going to be stuck with a bigger and bigger uncertainty in determining the momentum of that particle. You can't know its position and its momentum together at the same time really, really, really well. You can't have your cake and you eat it too. You have to choose. Do you want to know the position really well? Well, you're not going to know the momentum very well. Do you want to know the momentum really well and have a very, very small delta P? Then you're going to have to give up in having a whole lot of confidence in its position. There's always going to be uncertainty there. So the less uncertainty you have in one, the more uncertainty you're going to have in the other. This is the Heisenberg uncertainty principle. And again, it is a function of the act of doing science. It's a function of the act of measurement. It's a function of matter itself when we try to observe it using instrumentation or measuring devices. And so that's why we talk about the probability of finding this electron, because the very act of trying to find out where it is, there's always going to be some uncertainty. And oftentimes we talk about the probability of finding an electron 90% of the time within some region of space that we describe with geometrical shapes, like a sphere for the S first energy level, or those three-dimensional double eights going this, and one coming out and in for the 3p subshells and so forth. Remember that from chemistry? Here's part 2 of the Heisenberg uncertainty principle. And again, it has to do with measuring the amount of energy in a specific amount of time. And of course, anytime you have Planck's constant, 6.67 times 10 to minus 34th in the numerator, you're going to have very, very, very small values. And that's the Heisenberg uncertainty principle. Now, this does not mean that, let's come back to it for a second, that therefore we can't measure anything and all measurements are unreliable and therefore we should give up on doing science. What this does mean philosophically is you should not put your faith in science, because at the very heart of science, which is measurement and observation, there is an inherent uncertainty. Granted, it's very small, but there is an inherent uncertainty, not the kind of thing that should be the basis for somebody's faith. And that concludes our comments on Heisenberg uncertainty principle and chapter 27.